Welcome to iLectureOnline, and here's our next topic in physics called work, energy, and power. And all those really do belong together. You'll see in just a moment why. And to give you a feel of what that is, we have kind of a basic problem. We'll talk about the basics of work, energy, and power. We'll leave power to the side for now. We'll cover that in a later video, but we'll concentrate starting on work and energy at least. So by definition, work performed is equal to force times distance or displacement. And we are talking about vector quantities here. Force is a vector quantity and displacement is a vector quantity. And since we're multiplying together, we're going to do that via a dot product. And that's by definition. The work, of course, once you do a dot product, will be a scalar quantity. So work is just simply a number, but we do multiply two vector quantities together like that. So in this particular case, we have a force that's pushing to the right in the positive x direction, and we have a 50-meter displacement in the positive x direction as well. So the way this would work is that the force is equal to 100 newtons in the positive x direction, and we dot that or multiply with a dot product times the displacement, which would be 50 meters in a positive x direction. Now this will therefore become 100 newtons times 50 meters times x dot x. Now when you dot, too many dots. When you dot unit vectors together, you simply multiply the magnitudes times the cosine of the angle between them. So this will become 100 newtons, or why not go ahead and multiply this out. 50 times 100 is 5,000. So this is 5,000 Newton meters times the magnitude of the vectors, which is 1 times the cosine of the angle between them. But since they're both pointing in the same direction, the angle between them is 0, and the cosine of 0 is 1. So that simply becomes 5,000 Newton meters. Now, what is a Newton meter? Well, we have another unit for that. We call that joules, named after the famous physicist Joule, who discovered the relationship between mechanical energy and heat. So this work is therefore 5,000 joules. Now, what happens with that? So obviously, something or somebody has to provide that force. So let's say a machine or a person pushes this block for a distance of 50 meters and continuously pushes over a distance of 50 meters with a force of 100 newtons. So what's going to happen here? Well, we know that there must be friction because we're given the coefficient of friction. So let's figure out the friction force here. So if we do that, we can say we have the force of gravity pulling down on this block, which is mg. And then, of course, we have the reactionary force of the floor pushing back against the block, which is the normal force. And that will be equal in magnitude to this force right here. So it will be equal in magnitude to mg. Notice that they're equal in magnitude but opposite in directions, so those cancel each other out. However, you also have another force called the friction force, which will be opposing the motion. So it will be a force friction to the left, which by definition is equal to the normal force times mu. The normal force is going to be mg, so it's equal to mg mu. So part of the force, part of 100 newtons, is required to overcome the friction, and part of it, if there's any left over, will then be used to push the block, and of course that block will then be accelerated because that will then be the net force. So let's find out how big the friction force is. So force friction is equal to normal force, or I just write mg mu, which is equal to the mass of 5 kilograms times 9.8 meters per second squared times mu of 0.2, and 0.2 times 5 is that's exactly 1, so that means that the force friction is equal to 9.8 newtons. All right, and you see that that is in an opposite direction from this force right here. So 9.8 newtons of the 100 newtons is used to overcome the friction. The other 90.2 newtons is used then to accelerate this block. This block will then experience an acceleration. And when it gets to the end of the 50 meters, this block will be moving at some velocity, which of course at this point we don't know yet. So overcoming friction, let's write an equation that says work done to overcome friction is equal to force times distance, so force times displacement. And so the force required to overcome the friction force is, of course, 9.8 newtons. And so therefore we have 9.8 newtons in the positive x direction, because even though the friction force is pointing in the negative direction, the force to overcome the friction is pointing in the positive x direction. So the 9.8 newtons in the x times x direction dotted with the 50 meters in the x direction. So this will be equal to 50 times that, so that would be 98, that would be 490 Newton meters, x dot x, which is 1, and so this will equal to 490 joules. So we can see that of the 5,000 joules of work that was done, 490 of it was used to overcome friction, and the remainder will then be used to do work on the block by moving it to the right. Of course, what will happen then is the block will actually gain speed, gain velocity, and so what happens then is the remaining work, so W remaining is equal to the 5,000 joules of work we put into the block minus the 490 joules that we lost to overcome friction. So it's going to be 4,510 joules is remaining. And that work is then used to put energy into the block, and that will then turn into what we call kinetic energy. And so I like to write KE for kinetic energy, which means that 5,000 joules of work was put into the block, 490 joules was used to overcome friction, and of course when you overcome friction that then gets turned into heat, and we'll talk about that more later. And then the remaining 4,510 joules are then used to put energy into the block. So when you put work into an object, you put energy into it, and you can then either turn that into potential energy or kinetic energy. And without going into details at this moment what each one of them are, the fact that this block will be moving due to an acceleration caused by the net force, it will have motion, and when an object has motion, it has kinetic energy. And all of this remaining, here we go, 4,510 joules of energy or of work will then be turned into 4,510 joules of energy. In this specific case, 4,510 joules of kinetic energy. And so that's the basic concept, at least, of work and energy. If you do work on an object, either you use that work to overcome some friction force, or use that work to give energy to the system, either kinetic or potential energy. In the next several videos, we'll explain what each of them is and how to derive that. Okay, so this is the basic concept of work and energy. Power will come later in a later video as well.